Okay, this podcast is concerned with several unusual cases regarding the solving of trigonometric equations. Basically, a paper one approach and a paper two approach relative to variations on the tan function, which is a little bit unusual, not dealt with very often by IB, but let's see what we have here. So let's take a paper one approach to solving something like the sine over cosine plus cosine over sine being equal to 2. Note the unusual interval over which we're solving here, so keep an eye on that as a possible variation on the usual 0 to 2 pi or 0 to 360. It's not always the case that that's the interval involved. So one approach we can take here is to combine the fractions, and of course we need a least common denominator if we're able to add fractions together. So hence multiplying top and bottom of the fraction here to the left by the sine and the one to the right by cosine, so that you get a matching denominator, namely the product of those two, the sine times the cosine. In the process, we pick up sine squared plus cosine squared up top, which should ring a kind of a bell, because, of course, sine squared of an angle plus cosine squared of an angle, as long as the angles match, that, of course, sums to be 1. And so at this point, we could multiply both sides by the denominator here to look at it from this perspective, and, of course, 2 sine theta cosine theta being equal to 1. This you'll recognize as the sine of a double angle. So we've kind of worked our way into a pretty straightforward version of the sine of some angle being equal to 1. And if you actually think about the sine of some general angle being equal to 1, which is another way to look at it, would be to say that the angle in question, and in this case the angle is actually 2 theta, like twice an angle, that you could take and say, well, 2 sine theta is equal to inverse sine of 1. Well, if you can picture the sine curve peaking at 1, the first time it peaks at 1 is at 90 degrees, and then it kind of has this flow of plus 360, plus 360, plus 360. And so the 90 plus the 360 will put you here. You can back up from 90 to get that's negative 270, negative 360. So here's a spread of angles, dot, 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 such that the sine of that some general angle is equal to 1. And however, the angle in this case is twice theta, and so if twice theta is equal to each of these values you see here, then of course theta itself would be half of those. So you have to run the field here, so to speak, on getting the correct number of angles established here, so that when you have each of those, you've got all of the angles possible that'll be within the interval that's requested. Another take on the same problem, right, knowing that sine over cosine is, of course, tangent, so maybe right away you recognize, well, that's just tan plus, as it turns out, 1 over tan, because this would be the reciprocal of what's happening there. And so if tan plus 1 over tan is equal to 2, again, same interval, same problem, then multiplying both sides by tan will give you something like what you see here. And then you'll recognize, of course, that we have a trigonometric quadratic equation. So whenever we've got a quadratic, we pull everything over to one side and set it equal to 0. In this case, it is factorable, because tan theta minus 1 times itself gives you this when you expand it using the FOIL method. You can take the square root of both sides, and you're here, and then, of course, bring the negative 1 over. And so now we're talking about angles such that tan of the angle is actually equal to 1. So here you might start off by saying, well, there's a right triangle setting, right, 45, 45, 90, that allows you to get that the tan of 45 will be the ratio of 1 over 1, because 45, 45, 90 has a 1, 1, root 2 set of ratios to them. And so then we start to see a series of angles unfolding from there. So if you're dealing with tangent directly, which can be a little bit tricky to deal with, you've got to keep in mind what the tangent function actually looks like, right? It's not something that we see too often, but it has this sort of 180 degree or pi sense of period about it. And basically, if you're trying to solve where the tan of theta is equal to 1, think about the tan curves that you see here, and here's your y equals 1 line. And in fact, once you get that 45 degrees is one of the places that tan of like some angle, namely 45 degrees, is 1. And you can pick that up, again, from a right triangle in terms of the 1, 1, root 2, pretty straightforward ratios. Then you can really nicely see from the tan curve itself that once you've got some angle, namely 45, that has a tan of 1, well, the next one is going to be 180 degrees away from it, and back up from that one by 180, etc., because you've got this sort of pi or 180 flow to what's happening here, and of course you're undefined in these places with asymptotic behavior. So again, that was a case of just looking from a paper 1 perspective, several different ways of solving some variations on the tan function. Let's close with a paper 2 problem that would just be purely GDC based, very limited interval here in radians, you'll notice. And we want to know where all the x values are such that the function is equal to 0 within that particular interval. And if you graph this and start to look at how to zero in on what's happening, it actually is these 3 values right here. That'll be between basically 1.57 and 4.71 is what's happening there. So if you look closely at that, we need to be maybe blowing up the look on the GDC, or just modifying your window so you can see things a little bit better. And it's literally just a matter of finding 3 zeros. And so the talking point here would be that once you find a 0, and in fact there are 3 of them in play, once you find that first 0, just a reminder that that x value is currently stored in 2 different places on the GDC. It's actually stored in the second answer cell. So if you went back to the home screen and just asked for second answer, it would bring up that full value, which you could actually store. I've stored this in storage cell A. And then it's also in the X cell itself, which you'll notice on the GDC pad as well. So again, that 0 of 3.14ish is probably looking like pi. You can find that once again, once you get that particular 0 established using the feature of the GDC, then it's of course stored in second answer as well. And so you can always grab those values that are in second answer and you can store them somewhere if you wanted to in fact use those kind of values in other applications or in other settings within the problem as the problem extends on. This one doesn't, but it is good to start thinking more in terms of how can I put the GDC to work rather than writing down such long values. Just pull them out of the storage cells where they are temporarily, namely second answer, or like I said, they'll each be in the X cells, and you can dump them somewhere else so that you can have a series of these things saved up. Okay, good. That's it. Thank you.